Can you juggle a jam-packed schedule and still find enough rooms for every meeting? Meeting Rooms 2 is a Pattern Mastery 100 favorite and a must-know at Google, Amazon, and Meta. Over 35% of candidates get tripped up by overlapping intervals and efficient resource tracking. Master this, and you'll be set for any scheduling, heap, or interval-based interview problem. Let's break down Meeting Rooms 2 using the basic approach, so you can solve any resource allocation or interval overlap challenge step by step. You're given an array of meeting time intervals: start, end. Return the minimum number of conference rooms required for all meetings. List of intervals, unsorted, each as start, end. Integer, minimum number of meeting rooms needed. Picture running an event center. How many rooms do you need to make sure every meeting can happen without conflicts? Interviewers might ask, how do you efficiently track the maximum number of simultaneous bookings in a day? What's tricky? Intervals can overlap in complex ways. Tracking active meetings efficiently is key. Use a min heap to always know which room is free next. Sorting is crucial for an optimal solution. Sort all intervals by start time. Use a min heap to track meeting end times, smallest end time on top. For each meeting, if the current meeting starts after the earliest ending meeting, that room is freed, pop from heap. Otherwise, allocate a new room, push end time to heap. The heap size at any moment tells you how many rooms are in use. Let's clarify. Heap contains the end times of all ongoing meetings. Always pop from heap when a room frees up, i.e., when a meeting ends before the next starts. Edge cases. No meetings, 0 rooms. All meetings overlap. Need as many rooms as meetings. Sort intervals by start time. Initialize a min heap, priority queue. For each interval, if heap is not empty and interval starts greater than or equal to heap 0, earliest end, pop from heap. Push interval's end time onto the heap. After all meetings, heap size equals rooms needed. Now let's solve solution 1, the min heap approach for finding the minimum number of meeting rooms needed. We'll go step by step, explain each line, and understand why a min heap is the perfect structure for this problem. Time complexity is O(n log n, where n is the number of meetings. Sorting takes O(n log n, and each heap operation is O log n. The idea: store all end times in a minute heap. Sort all meetings by start time. For each meeting, check if the earliest ending meeting in the heap ends before the current meeting starts. If yes, free the room by popping from the heap. Allocate a room for the current meeting by pushing its end time to the heap. The heap size at the end is the minimum number of rooms needed. Think of it like tracking rooms. The heap always knows the meeting that finishes soonest. Line-by-line explanation of the code. We import Python's heappp module, which lets us easily manage a min heap. Think of it as a priority queue where the smallest element is always on top. We define our class solution. This is standard for coding problems. This function will return the minimum number of meeting rooms needed for a list of intervals. Sort all meetings by their start time. This ensures we handle meetings in chronological order. Imagine lining up events on a timeline. We create an empty heap. It will store the end times of meetings currently occupying rooms. The smallest end time is always at the top. We iterate over each meeting in order. We check if there is a meeting in the heap and whether the earliest ending meeting finishes before or exactly when the current meeting starts. If yes, that room is now free. Remove the earliest ending meeting from the heap, freeing that room. Think of it as a room becoming available for the next meeting. Add the current meeting's end time to the heap. Either it's a new room or a reused room. The heap automatically keeps the earliest ending meeting on top. The heap now contains all ongoing meetings at the end of the process. Its size equals the minimum number of rooms required. And that's how this algorithm works. It first sorts the meetings by start time, then uses a min heap to track ongoing meetings and room availability. Efficient, simple, and elegant. Sorting meetings is O(n log n. Each heap push or pop is O log n. The heap always tracks the meeting that ends earliest. Heap size at the end equals the minimum number of rooms needed. Let's test the function with intervals: 0, 30, 5, 10, 15, 20. Meeting 0 to 30 goes in the heap, 30. Meeting 5 to 10 overlaps push 10, 10, 30. Meeting 15 to 20 starts after 10 ends pop 10, push 20, 20, 30. Heap size is 2, so we need 2 rooms, and the program outputs exactly 2. We're going to look at solution 2 for finding the minimum number of meeting rooms needed. The time complexity of this approach is O(n log n, mostly because we need to sort the start and end times of all meetings. In this approach, we don't use a heap. Instead, we use 2 sorted lists, one for start times and one for end times. Think of it as lining up all meetings by when they start and keeping track of when each meeting ends. Then, we move through them one by one to see whether a new room is needed or an existing room can be reused. We start by defining a class called Solution. Think of it as a container that holds all the code for solving this problem. Inside the class, we have a function called min meeting rooms. This function takes a list of meetings, where each meeting has a start and end time, and calculates the minimum number of rooms needed. First, the function checks if the list of meetings is empty. If there are no meetings, it immediately returns 0, because no rooms are needed. Next, it collects all the start times and all the end times of the meetings, and sorts both lists. Sorting helps us process meetings in chronological order, like lining up events on a timeline. We then set 2 pointers, S for the start times and E for the end times, and also initialize a counter called rooms to keep track of how many rooms we need. Now, we loop through all the meetings. Each time, we compare the next meeting start time with the earliest ending meeting. If the next meeting starts before a meeting ends, that means rooms overlap and we need a new room. So we add 1 to the room count. Otherwise, a meeting has finished, freeing up a room. We move the end pointer forward to track the next meeting that will end. After that, we move the start pointer to the next meeting and continue checking. Finally, once all meetings have been processed, the function returns the total number of rooms needed. And that's how Solution 2 works. It first sets up the class and function, organizes start and end times, then uses 2 pointers to efficiently track overlaps and count the rooms. Simple, fast, and elegant. Let's check how our solution figures out the minimum number of meeting rooms using this test case. The input is 7, 10, 2, 4. Each pair shows when a meeting starts and ends. We sort the start times 2, 7, and the end times 2, 4, 10. The first meeting, 2 to 4, uses 1 room. The next meeting starts at 7, which is after 4 ends, so we reuse the same room. Total rooms needed is 1, and the program outputs exactly 1. Breakdown recap. We're given an array of meeting intervals, each with a start and end time, and we need to return the minimum number of rooms required so that all meetings can happen without conflict. In short, it's all about finding the maximum number of meetings that overlap at any point in time. Assess recap. The challenge is tracking overlapping intervals efficiently. Instead of checking every pair, we sort the meetings by start time and use a min heap to keep track of ongoing meetings by their end times. The heap helps us know which room will be free next. If a new meeting starts after the earliest one ends, we pop it off the heap. That room is now available. Otherwise, we push the new meeting's end time, meaning we need another room. The heap's maximum size during the process tells us how many rooms are needed. Structure recap. We start by sorting all intervals by start time. Then, we initialize a min heap to store end times. For each meeting, if the heap isn't empty and the current meeting starts after or exactly when the earliest one ends, we free that room by popping the heap. Then, we always push the current meeting's end time. Once all meetings are processed, the heap size equals the number of rooms required. Implement recap. We implemented this using Python's heap-key module. It ran efficiently, with a time complexity of O(n) log n, from sorting and heap operations, and passed all tests smoothly. Check recap. We verified the logic using multiple test cases. For example, 0, 30, 5, 10, 15, 20 needed 2 rooms, while 7, 10, 2, 4 only needed 1. Even edge cases like no meetings or fully overlapping schedules produce the correct results. Closing insight. The key takeaway? When dealing with overlapping intervals, sorting plus a min heap is a powerful combination. It's not just about detecting overlaps, it's about managing them efficiently, one meeting at a time.